This is PTA 4. Okay, so let us first see what exact syllabus we are expected of. As every week, we first check out the syllabus so that you can have exact idea. See, we have to see alkyl halides in which rearrangement reactions of alkyl carbocation. Now it says Grignard reactions, nucleophilic substitution reactions and their stereochemical aspects. That much for alkyl halide they have given here. And then aryl halides reactions in which Fittig, Wood's Fittig, nucleophilic aromatic substitution in haloarenes and substituted haloarenes excluding benzene mechanism and sign substitution. Again, here it is clearly mentioned exclude Grignard reagent. Okay, then comes the polymers, types of polymerization, addition, condensation, homo and copolymer, natural rubber, cellulose, nylon, Teflon, bakelite, PVC, biodegradable polymers, application of polymers, strictly related from the topic, not vague here and there, and 3 or 4 NCERT based JEE level questions must be given in the exam. Okay, so let's start from the most intriguing portion usually for alkyl halide chapter is nucleophilic substitution reactions. Let's just remove this. I have to check. I'm audible, I assume. And screen is, let me check, is already shared properly. Yes, shared. Okay, so let's start the work. If there is anyone new in the class, the method is usually I do not allow to unmute on your own. If you have any issue, please raise your hand. Okay, and usually I'll prefer to clear doubts in the end of the class. And the reason is because we have very limited time and all the students are there. So please write your doubts on some notebook or something. And in the end, I will stay back. Others can leave and those who have doubts can definitely stay back and I'll solve the doubts. Okay. So in case if anyone has any doubt, please hold it or keep it writing in some rough notebook or something. In the end of the class, we will discuss all those doubts. I hope that is absolutely clear, just to save time of each and every student who is in the meeting. And I request others who are like there, kindly avoid creating any type of nuisance. Okay. Sharing screen, video on karna, please avoid. Let's focus on whatever important for us this week. So, nucleophilic substitution reactions. Now, in case of alkyl halide, I will do the preparation properties, everything, but that is not so important. So, I am in fact starting the week preparation with nucleophilic substitution. So, if I say simply what is nucleophilic substitution, nucleophile attacks on RL, where L is what I want to say leaving group. Nucleophile attacks, right, like this, and L leaves, and as a result the product we formed is NUR and L minus is the leaving group. Leaving group is also sometimes called nucleofuge. This is our nucleophilic substitution reaction. Now, as far as the requirement in JEE is concerned, SN1, SN2, SNI, SNAR, SNAE, yes. And this especially I have written here, SNNGP and SNEA are not seen in mains, but SNNGP of course is seen in advance. In advance, we expect SNNGP for advance and we'll do it. We will definitely do NGP in our entire process. Neighboring group participation, that we will do. So SN1, as you know, 1 is for unimolecular nucleophilic substitution, SN2 bimolecular nucleophilic substitution, I is intramolecular nucleophilic substitution. AR stands for aromatic ring. So nucleophilic substitution on aromatic ring. SNAE is nucleophilic substitution through addition followed by elimination. And this is usually the property of acid derivatives. Acid chloride pay if you add ammonia or ester hydrolysis, they are all SNAE reactions. Okay, SNNGP, SNEA. SNEA is sign substitution, or you can say benzene, which we just saw is not in the syllabus. As far as advance is concerned, SNNGP is for advance, but benzene is not even in advance. So in case if you are worried about benzene, you can leave that. As per the JEE advanced syllabus of 2025, it was clearly mentioned excluding benzene mechanism. So you can definitely leave that particular topic. Now let us come back to what nucleophile is. So species which can act as a lone pair of electron donor, okay, will act as nucleophile. It could be negatively charged or it could be neutral. Example, ammonia, alcohol, RO minus, R minus, etc. These all are called nucleophiles. So basically nucleophile means nucleus loving species. Now comes the nucleophilicity, which is quite a problem with most of the time in questions. So first, factors affecting nucleophilicity. Nucleophilicity, what we mean is affinity for nucleus, well and good. But if I've used the word nucleophilicity, then I want to say specifically affinity for carbon del plus or carbon full plus. For such species we are talking of affinity, then it is nucleophilicity. Along the period, if we talk from left to right, both basicity and nucleophilicity decreases. Okay. Along the period from left to right, both basicity as well as nucleophilicity decreases. For example, CH3 minus is a stronger base as well as a stronger nucleophile. Then is the NH2 minus, HO minus, F minus. Similarly, amine is a better base as well as a better nucleophile than alcohol. Okay. Down the group, if we talk, down the group, basicity and nucleophilicity are opposite in order. Basicity decreases whereas nucleophilicity increases. This point is certainly with reference to protic conditions where solvation is there, then this point is valid. That down the group if we go, then nucleophilicity increases, because in case of carbon when we talk, then we talk irreversible donation of lone pair. So better donor is a better nucleophile, usually that goes under protic conditions. So I minus is a better nucleophile, then Br, then Cl, then F minus. But if we are talk of basicity, then F minus is a better base, then Cl minus, then Br minus, then I minus. Okay? Similarly, ammonia, phosphine, alcohol, RSH, and so on. ठीक, इसी सीक्वेंस में एक बड़ा ही फेमस क्वेश्चंस बच्चे करते हैं, तब उन्हें दिक्कत आती है कि फिनॉल वर्सेस PHSH. Okay, if we are asked Ka, then this is better, right? Why? PHO minus versus PHS minus. If we are asked stability, then this. If we are asked Kb, then PHO minus is a better base than PHS minus. If we are asked nucleophilicity, then less electronegative PHS minus is a better nucleophile. Is that absolutely clear? Okay. So down the group, if we are asked, then nucleophilicity and basicity under protic conditions, if we want to refer, then they are not identical. They run opposite. Okay. Let's move further. If donor atom is same, then nucleophilicity and basicity are same. If the donor atom is same, तभी ये बात true होगी. Only then this point is relevant. If the donor atom is same, then nucleophilicity and Kb are same. With increase in electron density, both will increase. For example, NH2 minus is a better base, better nucleophile than ammonia, than NH4 plus. This is in fact not even a base, not a nucleophile, right? OH minus is a better base, better nucleophile than water, than H3O plus. This is when donor is same. If the atom adjacent to donor atom has a pair of electrons, then due to repulsions, okay, its nucleophilicity will increase. For example, if I talk here, this is a better nucleophile, better, easy to donate as compared to ammonia. So this is what is the order of nucleophilicity. This is the order of nucleophilicity. If we would have talked of basicity, it is different. Okay. If we are talking of basicity, then hydrazine is a poorer base than ammonia. Now, on the same grounds, I can talk that HOO minus is a better nucleophile than this. Okay, it will be a better, stronger nucleophile. In case of halogens and enolates, this is particularly we are talking for them, though may be applicable to several cases, but again, with our limited orientation towards JEE, we should talk not in random chemistry terms. So in case of halogens and enolates, more solvation, less nucleophilic will be the center. Why? See, F minus and I minus both have single negative charge. But due to their charge difference, due to their size difference, F being smaller, second period element, will have higher charge density than I minus, right? F minus is small, I minus is big. So big, less charge density, water or any protic solvent I consider will be less surrounded on it because charge density is less. So 1 layer, 2 layer, 3 layer, like this I am expressing. Okay, less layers are formed. But if I talk of small ion, large charge density, then it will attract more number of solvent layers towards it. Okay, more number of solvent layers towards it. As a result, what will happen is that the structure, this whole structure will become embedded, very inside embedded than the solvent layer. When I want to use F minus as a nucleophile, I have to give extra energy required to remove this yellow covering over my F minus. Okay, which is the solvation. I have to remove this solvent layer, then only I can use it as a nucleophile. So that extra solvent layer removing energy is a problem for me. That is extra energy, which is making it as a relatively weaker or a poorer nucleophile than I minus. Okay, so under aqueous conditions, I minus is stronger than Br minus, then Cl minus, then F minus. Okay, though the charge density on I minus is less, but due to that solvation. Whereas if we talk of under aprotic or gaseous conditions, then when there is no solvation, they are just stripped ions. They are just ions with their charge densities, then definitely I minus having a larger charge density will attract the C plus or C minus, C plus or C del plus more than I minus. So then F minus is better than Cl minus, Br minus, I minus. This is in aprotic or gaseous. Enolates are also very important. For them also, if we consider C minus, O minus, resonance. But again, O minus will have more charge density as it is more electronegative. In the hybrid I'm talking, and then the water will surround it more. And if water will surround it more, again the same thing, that it will not be a easy point of donation under solvated conditions. So under aqueous conditions or polar protic condition, CH2 minus act as a stronger nucleophile, whereas under gaseous, when there is no solvation, O minus act as a stronger nucleophile. If the question doesn't mention anything about the medium, okay, if there is no mention of medium, then you can simply go by the idea of protic conditions. Okay, take it as a rule. If there is no mention of the solvent, always consider it as a protic medium and solve the question. Default. Okay. Now, rarely only, but yes, rarely, steric can also decide the nature of the reagent as a nucleophile. Whether it is a strong or a weak, steric can play a role. Because whenever I talk something as a nucleophile, it has to attack on carbon. If carbon is plus, then also 3 valencies must be present on it. If carbon is del plus, then so more steric, 4 valencies must be already present on it. Right? So steric is definitely an issue. Steric will be a problem. Now see tertiary butoxide. It is certainly a very stronger base than ETOK. No doubt about that. But is going to be a weaker nucleophile than ETOK. Tertiary butoxide act as a stronger base, and that is why with alkyl halide, you will prefer elimination products with tertiary butoxide, and substitutions will be considerable important in ETOK. Right? So this finds difficult to attack on carbon rather than H. Similarly, LDA, lithium diisopropyl amide. See, this is the structure, iso diisopropyl amide. LDA is stronger base than NNH2 but is a weaker nucleophile. Same thing जैसे tertiary butoxide, same way LDA is a stronger base than NNH2. But due to steric, weaker nucleophile. Now, steric inhibition of proton in aniline is an example of steric effect in basicity. So yes, even H plus can have that effect of steric. Because steric is with relation to space. So it is very objective thing where it is applicable, kahan baat ho rahi hai, right? Space is available or not. With respect to that, we decide steric. Now, H plus being small usually do not suffer, but I cannot say that H plus will never have steric. See, steric inhibition of proton in anilines is an example of steric factor for H plus. See, there are steric effects for basicity also. After discussing all this, we can conclude what is the difference in basicity and nucleophilicity. So whenever you talk of basicity, we always talk of Lowry-Bronsted basicity. That is reversibility. Okay. So basicity is always in terms of this Lowry-Bronsted. And there if you see, it is reversible. Whereas when you talk of nucleophilicity, it is irreversible phenomena. We do not consider that what product is formed is stable or not. We just donate the lone pair. Okay. If we talk of basicity equilibrium, where this is unidirectional, basicity, to compare basicity, we compare their K equilibrium, and to compare nucleophilicity, we compare their rate constants. Basicity is thermodynamically controlled and nucleophilicity is kinetically controlled phenomena. See, for example, if I talk of I minus attack H plus, yes, it is a very good attack KF because it is a large anion, easy to donate, so it is good. But the HI bond formed is weaker because of big energy gap between H and I. So KB is also very high. Now KF is high, KB is high, but for K equilibrium, what we talk is the ratio of KF upon KB. And we find that KF upon KB value is low. So we say KB of I minus is low. right? Whereas when I talk of nucleophilicity, I just consider this attack. Just K forward is considered. And as we talked, K forward is high. So nucleophilicity is high. That is it. We are not bothered about the bond energy of carbon iodine because we are not considering reaction is reversible in the given state, in the given conditions. I hope this is absolutely clear. This is the difference between basicity and nucleophilicity when we have to compare. Now let us talk about individual nucleophilic substitution reactions. First is SN1, unimolecular nucleophilic substitution reactions. As you all are aware that when this reaction takes place, solvent is an important factor, is a supporting factor for SN1. So water surrounds the RL in a way that whatever is L minus or minus pole of the substrate is surrounded by positive poles of solvent. And the positive pole of substrate is surrounded by negative pole of solvent like this, right? And such poles, which we just said are there, what happens is these plus and minus poles further polarize the RL bond because H here are there, they will attract the lone bonded pair towards them. O lone pairs will repel the bond pair towards L. So they are in fact helping, right? And when this finally happens, the gap, as this bond weakens, the solvent enters into the gap of R and L bond. Solvent separated ion pair is formed, and then gradually this solvent surrounds it and surrounds this and take away. So R plus and L minus is formed. And then on this R plus, nucleophile now attacks. But if I'm talking of R plus, it is going to be sp2 hybridized. So nucleophile can attack both from upside and downside. So if there is any chiral center, I will obtain it as a racemic mixture. Okay. Now, if you see this solvation will definitely release the solvation energy, hydration energy for water. This energy will try to compensate the bond dissociation energy of RL bond. Okay. So always remember the solvation energy will try to compensate the bond dissociation energy. Now carbocation is formed, so with increase in stability of carbocation, rate of reaction will increase. 3 degree RL, then 2 degree, then 1 degree. And MEL is definitely very difficult to participate in SN1. Even 1 degree we will not find very common. Okay. 3 degree, 2 degree are the commonmost for SN1. With increase in solvent polarity, rate of reaction will increase. Okay, because it will become easier and easier to form a carbocation. With increase in leaving group nature of L, rate of SN1 will increase. Poor base are better leaving groups. So for same alkyl, if I talk, then Ri, then RBr, then RCl, then RF. Because if I talk of Ri, then I minus is a better leaving group than Br minus, then Cl minus, then F minus. Clear? See. If this ion pair when formed and nucleophile wait for the formation of complete carbocation and then attacks, then it is SN1. But if nucleophile attack in advance or from backside here only, then it is SN2. Nucleophile attacks and this bond breaks, then it is SN2, L minus gone. Is that clear? Okay, so now this depends whether nucleophile will wait or not on the strength of nucleophile, which we have already discussed, that which will act as a strong nucleophile, which will act as a weak nucleophile. On those factors, this nucleophilicity will be affected by. Okay, so if we have strong nucleophile, then SN2 might be observed. Weak nucleophile, SN1 will be observed. Coming back to this, As free carbocation is formed, so rearrangement of carbocation will be observed. But that too certainly only when the new formed carbocation is more stable than the previous one. Only then you will have this stability or rearrangement of carbocation. Okay, that is a rule. Please take this very, very importantly, that carbocation rearrangement you will take only when a new carbocation is more stable than the previous carbocation. If this is not so, then never take rearrangement. I hope this is making some logic, but still I want to add few things. For example, here, see, this is a 1 degree carbocation. If I take this shift, I am having a 3 degree carbocation. So 1 degree, 3 degree with methyl shift. Okay, good. New form is more stable than 1 degree. Now here it is a 2 degree carbocation. Now it has two choices. It can go to 1 degree, it can go to 3 degree. But if I shift to 1 degree, the new form carbocation is less stable than 2 degree. So that is what I'm saying will never be observed. So I will only observe from here hydride shift and the 3 degree carbocation is formed. Okay, 3 degree carbocation is more stable than 2 degrees. So this is possible. Is that absolutely clear? So you have to be very clear always. If you have a choice and confusion where to go, first decide the direction of the shift, and from there whatever available groups are there, on that you decide the migratory aptitude which you studied in GOC. Okay, now coming here, see 1 degree, then it will rearrange to 2 degree, which happens to be benzylic also. So well and good, this rearranged carbocation will be formed. E1 will compete with SN1, and with increase in temperature, yield of E1 reaction will increase. So E1 will definitely compete with SN1, no issues about that. Okay. And if you increase the temperature, then only elimination will be dominating, as we have seen in alkene chapter. And for elimination, we need temperature. If temperatures are not given sufficient, then SN1 is faster and better. Direct bond formation, because for SN1, there is sigma bond formation, and for elimination, there is a sigma bond breakage to form a pi bond. So definitely the barrier, the level of difficulty for elimination is more. So SN1 is preferred over elimination. See, alcohol. Now, how to decide SN1 and E1? If I take HCl, I have a better nucleophile in the medium, which is Cl minus. If I take H2SO4, I don't have a strong nucleophile because it is HSO4 minus. So HSO4 minus is there, but is not a nucleophile. So ultimately, with increase in temperature, I can get alkene. With HCl, I have a Cl minus, which can act as a good nucleophile, immediate attack, formation of RCl, and thereby no elimination is observed in HCl. Is that correct? Clear? This is one more rearrangement, 1 degree to 2 degree to 3 degree. You can rearrange 1, 2, 1, 2, 1, 2, n number of times till you have your possibility of new carbocation stable than previous, stable than previous. But in this process of new stable than previous, please take this very clearly, that for ring expansion and contraction, see, this is 3 degree. And if I expand, I will get a 2 degree. Okay. So in ring expansion and contraction, usually the degree doesn't play importance. What is important is the ring stability. Okay, please take this clearly. For them, the important factor is ring stability, not the degree. Is that clear? So here, from 3 degree, you may see that I went to 2 degree. But it was not about the ring stability, it was about the it was not about the degree stability, it was about the ring stability. Clear? Moving to next point. So this was E1 and SN1 competition. If any chiral center is generated, as we have already discussed that the reaction proceeds by SN1. Carbocation is planar. So if a planar species is attacked by up and down, then of course it can be attacked from both directions. So racemic mixtures will be found, will be observed. Here, as intermediate formed is sp2 carbon. Thus, if any molecule fails to form sp2 carbon plus, then both E1 and SN1 will fail. कौन से हैं ये cases? Vinyl, phenyl, and the bridget. These three normally do not form sp2 carbocation or sp2 transition state if there is anywhere, and thus the reaction fail. SN1 is non-stereospecific. What was stereospecific? When I start with a specific stereoisomer of reactant and land to the specific stereoisomer of product, then the reaction is called stereospecific. But SN1 is non-stereospecific. You start with any enantiomer and you have the similar set of products. See, if I take this one, see, this is chiral. Whatever I take, ultimately it is converted to sp2. And then when nucleophile attack, I'll have a racemic mixture. So wherever I start, I am ending to similar things. So non-stereospecific and non-stereoselective. Weak nucleophile support SN1 over SN2. Ki effect is absent in E1 and SN1. What is Ki effect? That kinetic isotope effect. Heavier the isotope, reaction goes slow. So if I do the same reaction with hydrogen, I may observe 7 times rate of deuterium. That is kinetic isotope effect, but it is absent in E1 and SN1. I hope this type of revision of SN1 is clear. We will discuss that again when I start reactions of alkyl halide. So don't worry, this is the theory introduction. Moving to bimolecular nucleophilic substitution reaction. If I talk of bimolecular, it means 2 molecules will be there in the RDS. Now SN2, like E2, is a single step minima. Can be more step depending on the nature of L. Okay, otherwise it is single step. It is a good leaving group. Directly nucleophile will attack from 180° opposite to the leaving group. Here leaving group is going, nucleophile attacking 180° to the opposite side. And we have a sp2 transition state which is coordinated, which is penta-coordinated and very crowded. Nucleophile and leaving group will be exactly 180° to opposite, 180° opposite to each other, and they are on the unhybridized P. They are overlapping with that unhybridized P, whereas this, the 3H and the carbon, the green se jo maine triangle banaya, that is the hybrid orbital used. So sp2 hybridized transition state. So again, those things which will not be able to form sp2 transition state, planar things, wo SN2 pe fail honge. They'll fail for SN2. Okay. And when this thing completes, then nucleophile came from backside and L minus is gone. And what we can say, you can see this versus this is like an inversion of umbrella. So we observe umbrella inversion in SN2. Umbrella inversion in SN2 reaction, also called Walden inversion. It is also called Walden inversion. I am not saying that that inversion is of the configuration that R will become S, dextro will become levo. That we are not saying. We are just saying that umbrella is getting inverted. That is all. Nothing more than that we will add. Okay? Because R to S shift or dextro to levo, these are all group specific behavior. What is the group? Once that is decided, only then we can talk of what type of R to S or dextro to levo observation is true or not true. So we are not talking of them. Now, minimum one-step reaction, energy diagram. Of course, single step possible only when it is exothermic. Otherwise, why L will leave? Nucleophile will leave if the bond of nucleophile is weaker than L. Okay. So whatever we just talked, stereospecific and stereoselective. Inversion of configuration, Walden umbrella inversion, stereospecific, because you start with a specific reactant, you will have a specific product. Okay. Stereoselective, product can show stereoisomerism, and in the given reaction, if particular type of stereoisomer is obtained, then a stereoselective reaction also. No carbocation involved, so no rearrangement. Rate is dependent on RL into nucleophile. Highly sensitive towards steric factor on the carbon on which nucleophile has to attack. Order of reactivity of different degrees of RL if L is same. Now see, if leaving group is maintained same, then of course MEL with 0 steric will be fastest to react. Then any primary alkyl halide 2 degree and then 3 degree, which is supported by the relative order observed. MEL 1, then the 1 degree RL is 10 to the minus 2 ka order. 2 degree 10 to the minus 4 and 3 degrees 10 to the minus 5. So it is going slower and slower with increasing degree. Now, it is not just that you change the degree where the L is leaving. Even if you do not change the degree, but branching is introduced away from the RL position, like this remains 1 degree. This is 1 degree RL. This is 1 degree. All are 1 degree. But what we are doing, we are introducing the branching. See, alpha, beta, gamma. I can say this is gamma branching. No branching is best. Then I introduced 1 gamma branching. Then I brought it to beta. Right? I will not bring it to alpha because alpha will change the degree. I said degree is same. So this is again beta branching multiple. Beta 1 branch, beta 2 branch. So this is a neopentyl system, and this neopentyl system is practically very, very bad for SN2. Neopentyl, due to this bada sa big background, big cluster, will be very, very bad for SN2. Neopentyl, in fact, I will write never gives SN2. If compelled, how can we compel it? By increasing the temperature, making the conditions vigorous. Then it prefers SN1. And in SN1, we will see immediate rearrangement. As soon as this bond weakens, immediately shift. Okay, so we do not get a primary carbocation there at all. We directly get this carbocation and then the nucleophile attacks. So if ever you have any nucleophilic attack on neopentyl system, then it always prefers the pathway of SN1 and never by SN2. And the reason is simple: steric, steric, and steric. SN2 is highly sensitive to steric. Whenever it gets chance, it wants to avoid that steric. Okay, moving to next point. With increase in leaving group nature of L, of course, rate of SN2 will increase. Okay, both SN1 and SN2 fail when the molecule cannot form sp2 intermediate, matlab full carbocation for SN1, or transition state, that is for SN2. This we have just discussed. These 4 will not give these reactions so easily. Okay, this one also. Alpha halocarbonyl compounds are extremely good for SN2. Please remember that. Alpha halocarbonyl. See, this is carbonyl. This is the alpha position on which halogen, which is to be displaced, is present. Ester alpha position. ketone alpha position. Out of these also, as compared to ester, these are better. Ketone ones are better. Okay. So see alpha halo esters. Extremely good. Okay. Ki effect is absent. E2 competes with SN2. But the orders are different. SN2 order is 1 degree, 2 degree, 3 degree. And E2 order is 3 degree, 2 degree, 1 degree. So nature has its own arrangement. If the substrate is 3 degree, it will prefer E2 over SN2. If it is 1 degree, it will prefer SN2 over E2. And for 2 degrees, it depends what is the reagent. Please take, let me decrease smalls, take screenshot of this. This is from Claydon, and from this in internal exams, so many questions could be expected. Okay, please take this screenshot of this. Taken? Now coming to simple order. If we are talking of relative order, see how it is observed. MECl and benzyl are nearly equal, right? And vinyl chloride is faster than MECl and is faster than this 1 degree other one. And it's slower than MECl. So that resonance is not that effective. This vinyl is doing more of steric. Okay. 1, 2, 3, 4. Butyl chloride primary. Right. Say this allyl chloride is so very fast. Okay. Now coming to this, you see both electron releaser is also making SN2 very fast, and carbonyl coadjacent alpha position is also making it very fast. Okay, so this could be a question. Just see very, very observantly, or I'm suggesting take a screenshot. That would be better. See how much increase it is with respect to other 1 degree, or even see this 2 degree. 1 lakh times. Right? So what this jadoo of carbonyl or this? So there is an explanation of resonance in their molecular orbitals. Might not be required for JEE, but you have to remember that these reactions are extremely fast. Okay, alpha to carbonyl is very fast. Allyl and benzyl are nowhere close to alpha to carbonyl and oxygen ke alpha. These are nowhere close. See, 200, 1 lakh. Allyl 79, 1 lakh. Okay, so take this as a screenshot. Next comes the SNI, intramolecular nucleophilic substitution reactions with retention of configuration. Alcohol pe if I take SOCl2, SO2 HCl are gas. SOCl2 is called Darzon's reagent. Cleanest method for preparation of RCl because byproducts are gaseous. Like SOCl2, you can repeat the same concept with COCl2. So basically only 2 SNI reactions we do. Okay, the mechanism I am showing here, oxygen lone pair attacks, pi open. When pi comes, Cl minus gone. But conditions are gaseous. So it is never that alone Cl minus gone. Cl minus will immediately take H. So you will have practically HCl gone and this transition state form. Now see, if I talk of how it attacks like this. Intramolecular 4-member transition state, difficult. But yes, if it take place, then from where we are losing oxygen, same side chlorine is entering. So we will have very important point called retention of configuration. Same thing with COCl2 we can do. But yes, if you have taken pyridine as a solvent, then pyridinium chloride is formed. A free Cl minus is a stronger nucleophile, and therefore in SOCl2 in pyridine you have SN2, and in only SOCl2 then you take SNI. Okay, that is the difference. Then there are some few things like what is SN1 dash, what is SN2 dash, and what is SNI dash. Well, these all dash are just the reactions in which allyl is involved. So if I put here isotope and I react it with HCl, so what will happen? CH2 double bond CH, CH2 positive is formed, which can have resonance like this, positive, CH double bond CH2. And now when Cl minus attack, so I will have CH2 star per भी Cl का attack like this, right? And I can have attack here also. It is also known as allylic rearrangement. Yes, I am aware of the word. I'm using the term rearrangement. Yes. Morrison-Boyd. Morrison-Boyd uses this entire allylic resonance and term it as allylic rearrangement. I hope this is absolutely clear how they are taking allylic rearrangement. Is that okay, bache? ठीक, if there is any doubt, just keep on writing. Keep on writing. In the end, I will entertain. Don't worry. Okay. SN2 dash. Now see, let me exemplify some SN2 dash. Fixed thing. It has to be with this rearrangement type thing. But of course, as it is SN2, I cannot expect this rearrangement. So nucleophile is there. One thing it can attack directly here. Of course, that is what we are expecting. Nucleophile comes here. One more product will be very, very competent is what if this type of attack is there. And then this is removing Cl. Nucleophile. Now for me, there should have been no rearrangement, but there you have found a shifting of pi bond. Right? So we'll get mixture. Here also we are getting mixture. Is that clear? These are called SN1 dash. Coming to SNI dash. If I talk similarly for SNI dash. So for example, if I have CH2 star double bond CH single bond CH2OH and we treat it with SOCl2. So as we have already shown that CH2 star double bond CH single bond CH2O S double bond O Cl. Okay. We have just shown 2 pages back that how the transition state is formed. See, O S double bond O Cl in place of that. So that is what I have used. O S double bond O Cl. This is formed. Now, if I take normal SNI, this Cl should attack here. And then I will have a 4-member transition state, which is difficult to form. But see here, I will have a 6-member transition state. So in SN1 dash and SN2 dash, I talked of mixture of products obtained. But when we talk here, see, I will have no mixture obtained. This will be 100% sole product. There is no mixture of some attack here. Okay, so SN1 dash, SN2 dash, SNI dash are nothing but use of allylic positions in normal nucleophilic substitution reactions. उन्हीं को ही हम यूज कर रहे हैं, बस उसको कैसे यूज करना है is the point. So 1 dash and 2 dash में you can have a mixture, but in SNI dash there is no mixture. Reason 6-member. ठीक, I will still write no yield of CH2 star double bond CH, CH2Cl. This is not found at all because it proceeds with 4-member TS. Okay. Coming to other types, SNAE and SNEA, though not required this week, but if I could just introduce RCOCl. So if R dash is attacking, pi is opening. Okay. So see, RDS is addition. We have added the R dash. When this turns, Cl goes, and here is the product formed. Right? So this is elimination, but RDS is addition. This will do more detail in ester hydrolysis week. Okay. Then next comes the SNEA, benzene mechanism, which of course is not in the syllabus, just an introduction. NH2 minus if attacks like this, I have an anion, fluorine gone, I have got a benzene. Okay, this is elimination. And then on this elimination, we have addition of some nucleophile like ammonia. So this is addition. Clear? And RDS here is this elimination. RDS is elimination. Okay, not addition. Here RDS is addition. Here RDS is addition. And in SNEA, RDS is elimination. So if RDS is elimination, the reactivity order will be PHF, PHCl, PHBr, and then comes PHI. That will be the order, right? Because more the acidity of this positioned H, more will be the reactivity. Clear? Coming to important SNAR, nucleophilic substitution on aromatic ring. So we were doing SNAR, nucleophilic substitution on aromatic ring. If you want to do nucleophilic substitution on aromatic ring, see, it is very difficult reaction because this ring itself is electron dense. If nucleophile attack, then it will be repelled. So it is a difficult reaction. sp2 transition state intermediate from PHX we cannot form. So SN1, SN2 type things will fail. Nucleophile is being repelled. That is a problem. PHX bond dissociation energy is high. That is a problem. So overall, I can say that SNAR is a difficult reaction. It is not going to be easy to have SNAR. But if it happens, how it happens, let us see. Nucleophile directly attacks on the carbon where halogen is attached. Okay, so more the del plus on this position, more will be the attack, right? So this species is formed, which is resonance stabilized, right? Sigma complex of SNAR, or it is also known as Mesenheimer complex of SNAR. Aromaticity is lost, so definitely aromaticity will be regained. So if this goes back like this, then nucleophile X minus is gone. We have got the reaction. Now, as step 1 is RDS. Okay, RDS is step 1 when nucleophile attacks. So nucleophile will be repelled by electron cloud on benzene ring. Anything that could decrease electron density of carbon or increase del plus on carbon will increase the rate of SNAR. So again, see, the order of SNAR is PHF, PHCl, PHBr, PHI. Whereas for SN1 and SN2, the order was IBrClF. But for these reactions, that is SNAR and sign substitutions, the order is FClBri. Please remember this first. Okay, rate of SNAR will depend on both PHX and nucleophile. So it is a bimolecular reaction. Presence of strong electron withdrawing groups on ortho and para position of halogen will increase the rate of SNAR. Okay, this, which is called the Dow's process, this is not SNAR, this is benzene. Okay, this is not an SNAR reaction, this is a benzene reaction. chlorobenzene attacked by NaOH is a benzene reaction. If we go for this, see chlorine and NO2, NaOH we take, then OH and NO2, you will have SNAR. See the ease from 623 Kelvin to 443 Kelvin. If I introduce 2 nitros to leaving group, 368 Kelvin. And if I introduce 3, it becomes just so easy to displace, and I'll get picric acid. Very easy, as and as we are increasing the count of nitro groups. Right? Now let's move to something called NGP, neighboring group participation, also called n-chimeric assistance. NGP was suggested by these observations. Okay, like PHS CH2CH2Cl was 600 times faster than this. Though my expectation was sulfur is a minus I group, so it should be slower. Now this reaction is 3000 times faster than if pH was not present. TSO minus and this pi bond, if are present on opposite side, I am having 10 to the 11 times faster reaction if this pi bond was absent. And similarly, OTS and OAC, if are present on trans position, then it is 670 times faster as compared to cis isomer with acetic acid. Plus one more thing, if I take this alkyl halide, aqueous NaOH is there. Okay, so what is observed is a mixture of these, but what was expected was simple SN2, that chlorine should be displaced and this type of product should be formed. This was simple expectation that we can have such products formed, but we have a combination or a mixture of so many different products. Okay, in which you have a expected product also and other products also. Now, what are these other products? See, it appears that inversion ke saath saath same site attack retention. How is it possible? And it is an SN2, no rearrangement should be there. But third is some sort of rearranged product. Okay, third is some sort of rearrangement product. Chlorine is here, see, SET and chlorine exchange feel ho raha hai. So observation is 1, 2, and 3, which was very unlike, and that is how NGP came into scene. So how mechanism will be explaining NGP? So it says that sulfur attacks Cl, and this step is RDS. This I can say is intra SN2, intramolecular SN2 is taking place, Cl is gone. I have got a non-classical carbocation. Okay, and this non-classical carbocation, if is attacked by OH minus, correct? If OH minus is attacking on this one, then I am having retention of configuration product. But as it is SN2, so it can attack this side due to less steric, and it will give me a rearranged product. Is that clear? If water would have been used, 2 would have been major. If OH minus is used, then 3 is major. But ultimately, mixture is always there. Okay, so OH minus SN2, step 2 is fast. And this is how we explain the entire 3-product mixture to be formed. Now, the point with students is how would we know when to take NGP and when not? So always remember, in NGP, you will form 3-member ring and 5-member ring. 4 and 6 are not formed in NGP. And the intramolecular group should be there, which is sufficiently strong to have SN2, like this. Then only you will have NGP. For NGP, there has to be a group present in the molecule, having extra unpaired electron, and they should be sufficiently strong as a nucleophile. Then only you will have NGP. Like see, here sulfur can attack and remove, Nr2 can attack, O minus, bromine, and similarly this pi bond. And if I say pi bond, I can have a case where pH is there. though on next page it is there. As I said, 3-member ring. So you will have this type of attack. I said next page it is here like this. Okay, never take this side. That is wrong. 4-member ring. You will never be able to get the aromaticity again. Okay, now what are the possible groups which can be used for NGP? SH, S minus, SR, O minus, CO minus. All these groups written here are good for NGP. Remember, very important, OME. Do not participate in NGP when it is forming 3 or 4-member ring. There it does only minus I. For 5 or 6-member ring, it can do NGP. And a very important example of NGP is alpha amino acids when react with NNO2HCl. See, now what usually happen is we see carbocation formed and racemization. But with this, you form retention. Observation is enantiomeric pure product OH like this. And the mechanism is NGP. See, CO minus displaces N2. And then water attacks. So you have retention, a very, very important example for JEE. Alpha amino acids react with NNO2 plus HCl and we get retention of configuration. Now, what are the examples of SN1, SN2 reactions that we will see? See, alcohol react with HX. 1 degree alcohol, you will see SN2. For 2 degree, 3 degree, SN1. Okay, alcohol plus PCl5, SN2. PCl3, PBr3, these are SN2. SOCl2, SNI. SOCl2 in pyridine is SN2. Let's see examples. So, I think we won't be able to complete the entire lecture. Let's try how much we can. So, alcohol plus HCl, protonation happens. Right? 1 degree and methanol, then this method will be observed and then Cl minus attack here SN2. If it is 2 degree and 3 degree, you will have a carbocation and then attack. So Lucas reagent if used, concentrate HCl and ZnCl2, RCl formed is insoluble in Lucas conditions, so not aqueous conditions, in Lucas conditions. So the reaction is used to identify different degrees. 3 degree alcohol, instantaneous turbidity, 2 degree alcohol, turbidity after 5 to 10 minutes, and 1 degree alcohol, only after boiling turbidity is obtained. But note that these are 1 degree alcohols, but will give instantaneous turbidity because of their stable carbocation involvement. Okay? Alcohol plus PCl5. This is the mechanism and it is SN2. I'll share the notes. You can have it then. Okay. Please practice all these reactions. Like once you know how PCl5 works, you can use it for ether, aldehyde, ketone, acid, or epoxide. But a very important deviation from the usual path is amide on PCl5 gives cyanide, not the introduction of chlorine. It removes H2O and we get cyanide. Similarly, PCl3, PBr3, PBr, phosphorus I2, they all react by SN2 with all these reagents. SOCl2 we have already done. In case of ethers, again, HBr or HI, I'm sharing these notes with you, but is not this week's syllabus. You can read them. Okay. So, dilute H2SO4 में अल्कोहल में ब्रेक होना, HI-HBr में RI और अल्कोहल में ब्रेक होना, these are all substitution reactions. When to take which I have mentioned here. Coming to this week again, alkyl halides. So if I talk of alkyl halides, see these many reactions are there. Now how to decide SN1 करें, SN2 करें, elimination करें, कौन सा method करें? So aqueous KOH is OH minus and water is neutral oxygen donor. So this is a weak nucleophile. So you have SN1. Strong nucleophile you have SN2. Here it is a weak nucleophile. Here it is a strong nucleophile. So it is SN2. And here I would say it is a stronger base because less solvated OH minus is there. Clear? Now see, ammonia is a stronger nucleophile than water. Right? So I would say it is a stronger nucleophile. So this is happening. NNH2 is a stronger base. Alcohol, weak nucleophile. RO minus is a stronger nucleophile. So reaction is shifting to SN2. Observation, weak nucleophile SN1, stronger nucleophile SN2. Stronger base आ रहा है तो elimination आ रही है. Now see I minus is, अब डिपेंड करता है कंडीशन, इसकी कहानी थोड़ी अलग है, but I minus is quite a good nucleophile. So you are having this. Okay, Cn minus SN2, KNO2, AgNO2, SN2. LiLH4 is a strong nucleophile and a strong base. It is a strong nucleophile and strong base. So you have both SN2 and E2. Now, who will decide? Degree of alkyl halide will decide what will be the answers. RCO minus, stronger nucleophile, so SN2. R metal like Grignard, RLI, so SN2 and E2. Okay. So let's start. Alkyl halide plus aqueous KOH, SN2. And a nucleophile is OH minus. But remember, in NCERT, it is clearly given for 3 degree alkyl halide aqueous KOH is SN1. ठीक? Alkyl halide 1 degree, 2 degree or 3 degree with alcoholic KOH. It is always E2. Alkenes are formed. So order of ease of E2, 3 degree, 2 degree, 1 degree. An acting base is OH minus, which is less solvated in alcohol than in water. Ammonia SN2, you can have exhaustive methylation. Okay. First, this is formed, then again 2 degree, then 3 degree, 4 degree. Continuously, this is formed, but 3 degree, you will have alkene. NNH2 is strong base, so always alkene. Right? On the same track, we have written solvolysis when the solvent is acting as a nucleophile. Okay? Yes, very important. Finkelstein reaction. Now, what is Finkelstein? NaI in acetone. Here, the solvent is extremely important. See, acetone is aprotic solvent. So, in aprotic solvent, I minus is a weaker nucleophile than Cl and Br. So, these should attack. This reaction should go backward, but the balance that NaI is soluble in acetone, NaCl and Br are thrown out, are precipitate. So, by Le-Chatelier, reaction goes forward. Okay. Then comes the Schwartz reaction. Same, similar, SN2, AgF, Hg2F2, COF2, SbF3, they are taking the reaction forward. In case of ambidentate nucleophile, follow NCERT entirely. Don't follow Peter Sykes, don't follow big books, just follow NCERT. KCN, we get an ambidentate nucleophile C minus and N. So you should get attack of carbon as it is a less electronegative beta donor, cyanide is formed. With AgCN, isocyanides are formed because there is no dissociation. Rx plus KNO2, RONO, isonitro, AgNO2, nitro is formed. Rx, RCOAg, you have directly ester. Acid say SN1 say ester. Lithium aluminum hydride. H minus is strong nucleophile. So 1 degree, 2 degree, you can have alkanes. 3 degree will give alkenes by elimination. Okay. Alkyl halide with organometallic compounds like RNA, terminal alkyne se bane organometallic Gilman, you will have coupling product R and R dash. Right? And that brings us to the end of today's lecture. I'll share these notes. Tomorrow I'll complete Further, chemical properties of alkyl halides and other things, aryl halide, if anything left, preparation and all. Okay. So if anyone is having any doubt, please raise your hand. I will unmute you and you can ask me the doubts. Others, if they want to stay back and listen to doubts, most welcome, or else can start leaving. Yeah, please ask the doubts. Okay, I have Aditya. Yes, Aditya, unmute yourself.
Yes, ma'am. So
Yeah.
for the SN1 dash, SN2 dash, and SNI dash, how do you decide which of there's two products that are formed in every case, right? So how do you decide the major product?
How do you decide the major product? Did you ask that?
Yes, ma'am.
Well, certainly there are several factors to decide major product in those dash reactions that we just saw. Okay, let me add a little more as you have asked this particular doubt. So give me 1 second. I'll share how I decide. Of course, observations are there. In SN1, there is one effect called see, in SN1, I took this compound, if SN1 dash we are talking first, huh? And alcohol is attacking. So this site where the group left, that is usually the major, then the after resonance where it will be attacked. Though you can say that the plus density here would have been more. Now, why this is so? So solvolysis is usually SN1, and particularly if donor atom is oxygen with nitrogen as donor, it will be SN2. There is one thing called Aditya called proximity effect. Like here it is gone and the carbocation when formed, then solvent will immediately start attacking here itself in the TS, solvent separated. So when we talk of SN1 dash, then the resonated product usually is the minor, and from where the group left is usually the major. Okay. If I talk of SN2 dash, if we talk of SN2 dash, then this type of behavior is there. And now here I have taken both places attack. R dash, R, all this thing. Otherwise, then steric decides which place will be attacked more. Is that clear? That which place will be attacked more, direct attack or through pi bond attack will be more. So that thing is decided by steric. And SNI dash we have already discussed. Is that okay, Aditya? Was it Aditya or was it Ashish? I think I am addressing wrong. I was talking to Aditya. Yes, Aditya, unmute yourself.
Yes, ma'am, I understood. Thank you.
Okay, beta. So now moving to Ashish. Unmute Ashish.
Hello.
Yes, Ashish.
Well, you have mentioned that the hydrogen is more nucleophilic than ammonia. Hello.
Ashish, can you repeat yourself, please?
Ma'am, why the hydrogen is less basic than ammonia? My question is.
H is less basic than what?
Hydrogen.
H, hydrogen. I
No,
said
ma'am.
ammonia.
Hydrogen is less basic than ammonia.
No, I didn't say. Hydrogen is less basic than ammonia and it is a better nucleophile. Right. I said that.
Yeah. What is the reason behind the less basic nature of hydrogen?
Because if you form the conjugate acid, Ashish, then NH, the plus polarity that will be generated, if I am having an electronegative atom adjacent, NH 3 plus NH2 versus NH3 plus. This is more stable.
But it
As
has
compared to
low pair
hydrogen.
resonance. Okay.
Huh?
It has low pair resonance.
No, beta. How can there be resonance? Nitrogen octet is complete.
Okay.
Right? So
Yes,
there is no resonance. We are just having the inductive.
okay. Megaside.
Yeah. Clear?
Okay.
So that was Ashish. Ashish, anything more?
No, ma'am.
Okay. Okay. Anyone else? I'm waiting if anyone is there. Okay. Shubhangi. Yeah, unmute.
Ma'am, I have a doubt from earlier topic. Actually, we had a question on the Sunday exam. It was carbocation stability of heterocyclic compound. I think I can show the question. If
You tell me the question. Can you read it out to me?
Ma'am, it is like cyclohexane with an oxygen atom in it without the carbon, and then we have plus
Was
charge.
it the one in which it was asked which of the following is stabilized by complete octet thing? That was, you are talking of PTA 3 or what?
I'm talking about CTM 2 for Sunday's exam.
CTM?
Yes, ma'am.
Beta, then you have to tell. I don't have the CTM. So then तो तुम्हें ही बताना पड़ेगा मुझे. तो अब मैं एक पेज ऐड करती हूँ और तुम बोलो तो मैं लिखूंगी. Yes, now you tell.
Okay, ma'am.
What was the question?
Just it was like comparing stability of carbocation and
So you said one was a 6-member ring in which there was oxygen.
Yes, and one had sulfur.
Like this.
Yes, and then one had NH.
Same 6-member ring, na?
Yes, ma'am. And then on the
Okay.
adjacent, no, that's all these three, and we have plus charge. Yes,
Like
ma'am.
this.
Yes. So, ma'am, in my doubt is that oxygen will have back bonding with this with the plus charge. So shouldn't it be more stable?
So beta, wo to nitrogen will also have, na?
But then oxygen does better back bonding compared to.
This is wrong. This is wrong. If you draw the resonating structure here, see, this is what you will get.
Yes, ma'am.
And if here you will draw, what will you get?
O
Like
plus, okay, yes, electronegativity and.
So both are having the same thing. Nitrogen less electronegative will be a better bearer of this positive charge than oxygen more electronegative, na?
Right, ma'am. Okay, thank you, ma'am. That's all.